All right, guys. Welcome to Tuesday's pre-recorded lecture for July 12th. We're going to start with page 12 of lecture notes, week 12 and 13 on example 12. So this is page 11, example 12 that we're going to be working on. This is another application problem very similar to example 11. This one reads, the person bends at the waist with a straight back, making an angle theta with the horizontal. Then the force F exerted on the back muscles can be modeled by this equation, where W is the weight of the person. For part A, they want us to calculate the force F to the nearest pound, for W being 170 pounds and theta being 30 degrees. And so this is not too much using the identities, it's more of a plug and chug type of problem. So we're simply going to be replacing the W with 170 and theta with 30 degrees. And you'll get an expression like this. Okay, so 0.6 times the weight of 170 times sine of 30 plus 90, which I've simplified here on the right into sine of 120 degrees. So from there, you would just simply punch it into your calculator. So 0.6 times 170 times sine of 120 divided by sine of 12 degrees. You want to make sure that you are in radian mode, in degree mode. So once you've checked that, you can go ahead and calculate, and it's going to give you approximately, rounded to the nearest pound, that's 425. Well, this force is in, the W was given in weight, so the force is also being, going to be in units of pounds. Okay, so we're going to have 425 pounds approximately for the force. Okay, the second part, part B, is asking us to use an identity to show that F is approximately equal to 2.9 W times cosine theta. Okay, so in order to change this equation into something involving cosine rather than sine, we're going to have to rely on our co-function identities, because those are the ones that relate sine to cosine by means of in this case, subtracting away from the 90 degrees or pi over 2 radians. Okay, so let me just write down the formula first of all. We have a co-function formula that says sine of 90 degrees minus theta is equal to cosine of theta. Now clearly that's not what I have. I have theta plus 90, so we're going to have to figure out a way to write it as a minus here so that we can apply the formula. So let's see. The force is equal to 0.6 W times times sine of theta plus 90. I'm going to first of all switch the order. Okay, so 90. You can think of this as 90 plus theta, but I'm going to write that plus as a minus a negative theta. Okay. So I did two things. I switched the order because it was in theta plus 90, so I changed it first to 90 plus theta, and then I wrote the plus as a minus a negative over sine of 12 degrees. And just so that you don't get confused between this theta in the formula and the co-function formula versus the theta given in the equation for force, let me change this variable into a. Okay. Now, according to the co-function formula, if you have 90 minus some angle, that is going to be the same thing as cosine of the angle. So in this case, 0.6 W, the sine of 90 minus the angle is going to become cosine of the angle. So in this case, cosine of negative theta, because A corresponds to this negative theta. Okay, and now we still have over sine of 12 degrees. Now, cosine of negative theta, we know that cosine is an even function. So even functions, if you have negative in the argument, you can ignore it, it goes away. So we still just have cosine of theta. Now in order to get this 2.9, so I'm just write the cosine theta. In order to get this 2.9 W, we can take the 0.6 over sine of 12 and simplify that. So what I'm going to do here is write this as 0.6 divided by sine of 12 degrees times W times cosine over 1. Okay, so I'm simply grouping these together. Okay, we would still have the same expression. So from there, let's punch it into the calculator. 0.6 divided by sine of 12 degrees. That is approximately 2.9. Right, if we round to the nearest tenth place, that would be 2.9. And then W times cosine theta over 1, that's simply W cosine theta. Alright, so we made it to the goal of 2.9 W cosine theta. Now part C is asking the question, for what value of theta is F maximum? Meaning, when are we going to feel the most force on our back muscles as we are bending over at the waist? So just intuitively, if you try bending over, you're going to feel that you're going to feel the most force when your back is horizontal to the ground, right? That's when you're going to feel the most force on you. Mathematically, that makes sense too, because notice the force is approximately 2.9 W cosine theta. So this attains a maximum when cosine attains the maximum. Let me just write that. So F being approximately 2.9 W times cosine theta attains a max when cosine theta attains the max value of 1. Now, when does that happen? Well, cosine is going to be, at 0 degrees is 1. So that happens when theta is 0 degrees. So at that point, we're going to have F is approximately 2.9 W times cosine of 0 degrees will give us 2.9 W times 1, which is just 2.9 W. So approximately there's 3 times your weight worth of force that your back muscles are undergoing. Again, just to make sense of this, if you're still a little bit iffy about what this is representing, let's say that this is you standing upright relative to the ground. At that point, your back muscles do not experience any force due to bending. But if you start bending, and actually, let me draw this a little bit taller. So if you start bending at the waist, they're talking about what is the angle that gets formed relative to the horizontal line passing through your waist. Okay, so here would be 90 degrees, but if you're completely bent over at the waist, that angle is going to be 0 in comparison to this horizontal line. So at that point, you'll feel the full force. Okay, moving on to some different type of problems. We're now going to take a look at graphing problems. And we know how to graph at this point nearly all trigonometric functions, or I should say any kind of shift or any change in amplitude, any change in period, we know how to graph. In this case, they're giving us something to graph which has some trigonometric functions, but we have sine squared, cosine squared involved, and the angle is also changed, just x over 2. I mean, this is not too bad because we know that anytime x has a coefficient, that's just going to be affecting the period. But what we have never seen before is a product of trigonometric functions, especially if they're squared. So instead, what we're going to try to do is apply some identities to help us rewrite this in a way that we have graphed before. Now this one's a little bit tricky, and by all means it's not intuitive at all, but well, first things first. Remember how I told you guys whenever there is too much going on in the argument, like if the x is being divided by a number or multiplied by a number, you can always replace it with a single variable. So in this case, I'm going to let a represent the x over 2. That way I can focus on the bigger picture of what's going on outside and simplifying that. So I'll have this become y equals 1 minus 8 times sine squared of a times cosine squared of a. All right, and on this next part is to notice that both the sine is receiving the square and the cosine is receiving the square. So it might be a good idea to try and write this as a single base raised to the power of 2. In fact, we can go a little further and also notice that this is a 2 times a 4. So I could potentially write this as a 1 minus a 2 times a 4, which we can write as a 2 squared, times a sine squared of a times a cosine squared of a. Again, by all means, this is not intuitive, or you don't get to see this right away. But a little bit of trial and error will help you see that this is a good step to take. Reason being is that now I can write this as 1 minus 2 times 2 sine of a cosine a, and write the square outside parentheses. Remember, we had that power rule that when you take the square of the product of several factors, each of the factor receives a square. Okay, so in this case, I'm just taking the square from these 3 factors and pulling it out. Now, why would I want to write it that way? Well, notice that this 2 sine of a, cosine a, that can be collapsed into one trig function by applying the double angle formula. 2 sine theta cosine theta is sine of 2 theta. So what I'm going to do here is write this as 1 minus 2 times sine of 2 times the angle, which is a. And I still have that square out there. So even though it's still not completely simplified because I still have that square, at least it's nice that I no longer have both sine and cosine. I only have sine now. Okay, so sine of 2a. How do we get rid of the square now? Again, take a look at double angle formulas. If we look at the formula for cosine of 2 theta is equal to 1 minus 2 sine squared theta, that matches directly or almost directly to what we have, right? Except that instead of having theta here, we have angle 2a. Okay, so I'm going to be applying this third formula with cosine 2 theta. This becomes cosine of 2 times the angle, which is 2a. And that is just in turn cosine of 4a. Okay, so we're almost at the point where we're able to graph this, because now we have y is equal to cosine of 4a, but a was representing x over 2, so let me just go in and write that. That's y equals cosine of 4 times x over 2. The 4 and the 2 cancel, and a 2 is left over. So in reality, what we're graphing is cosine of 2x. Okay, now that I know how to graph, that I know has an amplitude of 1, okay, because the a is 1, so that means that we have amplitude of 1, and there is no reflection about the x-axis. Since the b is 2, that means that the period is going to change. Instead of being 2 pi, it's going to be 2 pi over b, meaning 2 pi over 2, which is just pi. And then our step size is going to be a pi over 4. There is no horizontal translation, no vertical translation. Nothing is being added outside of the argument, outside of the cosine function. So to graph it, we first label our tick marks, pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, and 4 pi over 4. We're going to have an amplitude of 1 with no reflection. So let that be 1, and this be negative 1. And then at 0, cosine begins at 1. Again, if you forget this, that's okay. You can just plug in the 0 into the function. Okay. So we would get a 1. Then at pi over 4, we're going to reach 0. At pi over 2, negative 1. At 3 pi over 4, 0 again. And then at pi, let me just reduce this down to pi, we're going to make it up to 1. All right. So I just want to walk through the steps one more time in case anything was a little confusing. The first thing we did was rewrite the x over 2, replace it with a, so that we can focus on what's happening outside of the argument. Okay, so I got 1 minus 8 sine squared of a cosine squared of a. From there I said, let's write this as 2 times 4, because 4 is 2 squared, and then we already have a sine squared and cosine squared. That way we can take out the square from these 3 factors. Okay, so I'm going to end up with 1 minus 2 times a 2 sine a cosine a with the square outside parentheses, because each of these was originally squared. Why did we write it that way? Well, because this 2 sine a cosine a becomes sine 2 of a under the double angle formula for sine. Okay. So I'll try to fit it in there. This was double angle formula for sine. All right, so we get sine of 2a squared. Now from here to this step, that's where it might get a little bit harder to see. This whole expression, okay, the 1 minus 2 sine squared of some angle A, is the double angle formula for cosine. Now there's 3 of them, and I want to do this on the side, match it up, because this is a common question that I get when I'm holding live lectures. How is that the same thing as cosine of 2 times 2a? Well, again, let's pretend that instead of having 2a here, that I just have some other angle. Let's say that I have an angle C. I'm going to let C be equal to 2a. Then this green expression that I've underlined is 1 minus 2 times sine of C, and this part is squared. Now, whenever we have a square of a trig function, we have another way to denote it. We can also denote it as sine squared of angle C. Now this looks exactly like the double angle formula. In the double angle formula, we have that 1 minus 2 times sine squared of whatever the angle is equal to cosine of 2 times the angle. So this here is going to be cosine of 2 times the angle, which is angle C, this angle here. But now C was representing something, it was representing this 2a, so we can bring it back in. And that is how we get to this point here. So again, I'll try to squeeze it in there. This is the double angle formula for cosine. It's the third double angle formula. All right, then from there we simplified. 2 times 2a gives us cosine of 4a. And then from there we said, well, a was representing this x over 2, so we brought it back in. Take 4 times x, you get 4x divided by 2, you get 2x. So ultimately what we're trying to graph is this y equals cosine of 2x. Now from there, you just apply the usual rules that we know for graphing from our set of lecture notes week, I believe it's 8 and 9, or 9 and 10. But I also want to show you on Desmos how this graph is the same as the one that we get for 1 minus 8 sine squared cosine squared of half the angle. So let me just bring up Desmos really quick. Okay, so I'll be graphing 1 minus 8 sine squared x times cosine squared x. Okay, and it seems like I have a bit of an issue here. Let's see. These parentheses around the sign. Okay, so I think what they want, let's see. I'll probably have to write it. I might have to write the square outside. Let's see if that changes things. Ooh, that looks cool. Okay, so I've got that, and then let me just change the x and y axis so that it focuses only on what we graphed, which was from 0 to pi. Okay, and then we have a step size of pi over 4. And for the y-axis, we're okay with just having, let's see, we're okay with just having these. Okay, so it seems like we might be having something a little bit different. Oh, that's because I forgot to write x over 2. Hold on. This should be x over, well, okay, x over 2. X over 2. There we go. Okay, now it looks like ours. Okay, so at 0 we reach 1, at pi over 4 we reach 0, at pi over 2 we reach -1, then 0 again at 3 pi over 4, then 1 again at pi. Okay, for example 13b, this one's slightly a little bit more involved and complicated. The work is quite long, so I'm only going to work it out partially and then give you the rest as part of the reflection assignment with some hints. Okay, so we're going to start off by writing this tangent function in terms of sine and cosine, since I do have this cosine squared that is part of the equation. Maybe that way some of the terms can simplify. So tangent becomes sine over cosine. And we have times cosine squared x minus 2 times sine over cosine again, all over a 1 minus sine over cosine. And the tangent is squared, so we're going to be squaring the term. And then we have plus 1. Okay, so simplifying a little bit. The cosine squared over 1 multiplied with the sine over cosine, this cosine will cancel and this square will cancel, because essentially we have cosine times cosine. So one of them is going to divide out to a 1, and we're going to end up with a 4 sine x times a cosine x minus a 2 times sine x over cosine x, all over a 1 minus sine squared x over cosine squared x. Okay, now I'm going to leave a little bit of room there, because the next thing that I want to do is I want to go ahead and cancel out some of these fractions, because I don't like having complex fractions. So I can see that the least common denominator between cosine x and cosine squared x is going to have to be the cosine squared x. That way I can cancel that fraction in the denominator. And so at the top, I'll have to distribute cosine squared multiplied with the 4 sine x cosine x. That is going to be a 4 sine x cosine cubed x. And then 2 sine x cosine x times a cosine squared x. One of the cosines will cancel, and we'll end up with a 2 sine x cosine x. And the denominator, if we repeat the process, distribute the cosine squared to the 1, and we get cosine squared x. Distribute the cosine squared to the sine squared over cosine squared, and we get just the sine squared x. And then I won't forget my 1 here. Okay, what can we do after that? Well, I noticed that these two terms have a greatest common factor of 2 because of the 4. So the greatest common factor between 2 and 4 is a 2. The greatest common factor between sine and sine is sine. And the greatest common factor between cosine cubed and cosine would be a cosine. Okay, so I'm going to factor that out and see if it helps me simplify anything at all. Okay, so I'll take out the 2 sine x cosine x, and I'll be left with 4 divided by 2 gives us 2. Sine divided by sine is just 1. Cosine cubed divided by cosine gives us a cosine squared x. And then minus, well, here everything's going to divide out to 1. Right? You can always verify whether or not you factored this correctly by distributing back in and making sure that you get this original expression at the top. Okay, we have over cosine squared x minus sine squared x plus 1. Okay, so this is the part where I'll stop, and I will give you guys a hint as to how to proceed to it. Take a look at your formulas and identities and see if any of these 3 expressions can be replaced by a simpler form of the expression. And once you do, it should simplify nicely to something of the form y equals just a single trigonometric term plus 1. So I'll let you guys work on that during the reflection assignment. Well, some last comments I want to make regarding identities, trigonometric identities, is I want to make sure that it is very clear to us what the difference is between an equation and an identity. So I'm going to write that down on a separate sheet of paper. And we're going to have what is an equation versus what is an identity. Because on our sheet, on our formula sheet, all of these look like equations, right? And there's been times when I've referred to them, well, not these specifically, but to the ones that they gave us in the examples, I've referred to them as equations. And then once we've done proving them, or proving that the right-hand side is equal to the left-hand side, then I call it an identity. So what exactly is the difference? Okay, well, an equation is an expression that is true conditionally, so I'll just say that shorter terms. This one is true conditionally. So, i.e., this one is true only for certain values. I'll give you an example. Let's say that you have the equation 5x plus 1 is equal to 11. Well, this is an equation because this one is true conditionally when x is equal to 2. Right? When x is equal to 2, we're going to have a 5 times 2, which is 10, plus a 1, which is an 11. So we'll have 11 equals 11, and that, well, that is equal. It's not going to be true for all of the values. So if I try to plug in any other value, let's say I don't know, let's say like 10, for instance. What am I going to get there? Well, I'm going to get a 5 times 10 plus 1. Is that equal to 11? Well, here I'm going to have a 51, right? And that does not equal 11. So it's true for only certain values. of x in this equation. Now, what about an identity? Well, an identity is true universally. And so by universally, I mean it's true for any value that you replace the variable with. And so true for any value replacing the variable. Again, I'll give you an example. If you've seen this before, the perfect squared trinomial identity, you have x plus y squared, that is always going to be equal to x squared plus 2xy plus y squared. So for instance, let's try x being, let's say, like 3 and y being, let's say, -1. And I'm making these values up. You can make some different ones up if you'd like to check. But if I do 3 plus a -1 squared, that is going to be a 2 squared, which is a 4. Then if I look at the right-hand side and plug in those values, it's going to be a 3 squared plus a 2 times a 3 times -1 plus a -1 squared. That gives me 9 minus a 6 plus a 1. 9 minus a 6 gives me a 3 plus a 1, that's 4. Okay, so you can see that both of these are the same value. Now, why does x squared plus y squared give us x squared plus 2xy plus y squared? Well, that's simply because we distribute, right? If I were to carry out, and again, here I only tried 2 examples, right? So that doesn't completely prove the identity. It just proves that it's true for these 2 values. And if we're saying it's an identity, why is it true universally? Well, I'm about to show you why it's true universally. Because you can just simply distribute. X times x gives us x squared, x times y gives us xy, y times x gives us xy, y times y gives us y squared. And so combining the like terms, this gives us x squared plus 2xy plus y squared, which is the right-hand side of the identity. So that is the main difference between equation and identity. One of them is only true for certain values, okay, the equation. The identity is true regardless of what you replace the variable by. All right, so that'll be the end for today's pre-recorded lecture. Please make sure that you complete the reflection assignments and the relevant homework exercises on my lab. Have a wonderful rest of your day.